back.
Right.
Well, good afternoon, everybody. Glad to see so many people here. Before I start, I should say that after this, there'll be drinks on the fifth floor of the Maltese Engineering building next door, so you can come and discuss ideas and so forth with Radia. So, I'm Mark Handley. I'm President of Network Systems here at UCL, and it's my great pleasure today to introduce Radia Perlman. I've known Radia for many years now. I think we first had a lot of interactions about 15 years ago about IP multicast, which is a technology that I don't think any of us managed to get right. But Radia over the years has got many network protocols right. Radia worked on routing and security for her PhD thesis on the interaction between those two. She's the instigator of the spanning tree protocol, which is how large lands around the world are built out of segments. Radia's worked on link state routing, on updates to that, applying it to land and so forth. And also Radia's done a lot of work in the area of network security. So through all of that work, she's got a very good viewpoint on how network protocols design what succeeds, what doesn't succeed, and so forth. And so Radia today is going to give us a talk on the folklore of network protocols and give her our insights into how network protocols are designed, built, work, fail, etc. Radia.
Thank you. So, okay. So, yeah, network protocols. A lot of what everybody knows is actually false. You know, what happens is somebody says something and then other people repeat it and you hear it so much you feel like really stupid even sort of questioning it. But please, I want people to think skeptically. So the way networking tends to be taught in most books, not my books, but in other people's books, is as if TCP/IP arrived on tablets from the sky in its awesome perfection. Nothing else ever existed. And you know, they're kind of telling students, memorize these RFCs. And I think, you know, and the only time they sort of mention anything outside of that stack is just to kind of sneer at it, because, you know, anyone not involved in this particular standards body are just complete morons or whatever. You know, that's not the way that I think things should be taught. I think instead you should focus on conceptual things, and this is the way my books are, where I say, oh, you know, here's a problem, here's 7 different ways I could imagine approaching it, and by the way, you know, IPX worked this way, AppleTalk worked this way, and so forth. And it's interesting, my publisher fed back to me that some professors say, why are you talking about AppleTalk? My students don't need to know about AppleTalk. As if students have this very, very tiny amount of memory. And if you fill it with any information that is not on a recruiter checklist when they say, you know, do you know about this, do you know about that? No recruiter is going to ask them if they know about AppleTalk. So they've wasted these precious brain cells of the students. And I actually think if the only thing you really care about is IP, you will get a much deeper understanding of it if you know, if you've seen alternatives as well. So, you know, that's the kind of thing that I'd like to do. But things are incredibly confusing. When you're trying to compare technology A versus B, just so that I won't step on my punchline here, you know, I like to get to the heart of it. And so you get these 2 600-page specs, and you're trying to see what's actually different between A and B. And unfortunately, nobody really understands them both. Oh, yeah, so I tell people that what you would like to believe is like people in standards bodies are well-educated technologists that are carefully evaluating engineering trade-offs of various things. And I say actually a much more accurate way to think of it is as drunken sports fans. It's like my team versus the other team or whatever. So when you're comparing technology A versus B, nobody understands both. So you hope to, like, looking at these 600-page specs, you hope to save yourself some time. You go to someone who's an expert in A and say, how does it compare with B? And they say, well, A is awesome and B sucks. And yes, you know, of course. And then somebody mumbles some sort of vague marketing thing and everybody repeats it. But then you figure out some things about B that are better. And you go to the A people and you say, actually, B has all these features. And it's like, no problem. They steal the ideas. And so now you have these two moving targets. And what is actually the intrinsic difference? So one thing you could do, let's get down to facts. What if you actually measure it? And people do this all the time. So they measure technology A versus B. And they say, A, it takes more power. Whatever, A has more latency and stuff. Well, I never believe that unless I can think about what's intrinsic about A that would cause it to have more power. Because even though it seems so scientific that you're actually measuring two things, what are you actually measuring? You're not actually measuring technology A versus technology B. You're measuring one implementation of technology A versus one implementation of technology B. So the worst example of that I saw was somebody was showing with technology A that you only got 1 gig of throughput. With technology B, you got 4 gig of throughput. And it's like, wow, throughput is like a good thing. But I couldn't for the life of me figure out what would make technology A have less throughput. And so I said, were you using a 1 gig physical link when you were measuring A? He said, yes, that's all he could find in the lab. It's like, then you don't put it on a slide. There's no truth there. It's like, anyway. So yeah, the way that I wish that things would be compared is you isolate the various conceptual pieces rather than looking at two 600-page specs, and you say, what are the various ways in which they kind of differ, and then for those things, look at what the pros and cons are. And so now I'm going to talk about some really confusing stuff. People talk about, should you use layer 2 solutions, or should you use layer 3 solutions? And they sound like they know what they're asking, but this actually makes no sense whatsoever, and I'll explain why this is sort of a nonsensical way of putting it. So what's all this thing about layer 2 versus layer 3? So what is a network protocol? It's sort of the basic idea is you put your data in an envelope and you address it. So you have a source and a destination. And there's a switch that takes in a packet, looks at the envelope, has a forwarding table, and decides based on the information in the forwarding table how to move the packet around. I mean, it's like that's what all of them do. So a switch is something that takes in data and forwards it. And so it can be a bridge or a router or a switch. And it's, like people that try to make distinctions in these terms. I'm not going to make distinctions. I'm just going to call it a switch because, sort of stealing my thunder a bit, layer 2 and layer 3 are the same thing. To say, well, a router is a layer 3 thing and a switch is a layer 2 thing, or unless you call it a layer 3 switch, I don't know. So it's just sort of simpler to just call the thing that moves the data around a switch. So what does a switch do? It forwards based on information in the envelope of the packet, and which can be a destination address, like it is in IP or Ethernet, or it can be a label, like MPLS, and I'll talk what those mean, and I'll also compare them about, what are the pros and cons. And if you need to keep things in order, your forwarding table might say, for this particular packet, you can send out any of these 4 ports. But if conversations have to stay in order for whatever reason, it annoys me that they do, but if they have to stay in order, then you have to look at other things in the packet so that for the same conversation, all of the packets go the same way. Okay, so when does the forwarding table get filled in? Well, it could be filled in proactively. That means you fill in all the switches tables so they'll know exactly what to do with any packet. Or you could do it when a flow starts, which means that the switch only knows how to handle the current conversations going on, and if it sees a packet for a new conversation, it goes, oh my goodness, I have no idea what to do with this, and then it has to go find out somehow in order to get this extra table entry. And I'll talk about, the pros and cons of these things. But these are the dimensions in which kind of network architectures can change. So yeah, it seems to me, and when I say seems to me, it's like this is a great opportunity for academics to kind of study it. And seems like proactively would be better, that filling in the switches with information so they know exactly what to do with anything that they're going to see would be better than having to panic when you see something new and have to somehow acquire the entry, because then you have this delay before you can start talking. So information in the packet. The forwarding table could be based on a destination or a label or a flow, and I'll compare these things. And the forwarding table either gives like a single port, or it gives a choice of ports, and you allow the switch to decide how to multipath the stuff. And so as a preview, I think doing it based on a destination rather than like a label like an MPLS, I think is always better. And I think it's better to have the switch have a set of ports and let the switch decide how to move it around rather than some central entity. But I'll get to that. So if you have a destination address, again, there's sort of dimensions in which it can differ. The destination address can be flat or hierarchical. What does that mean? Flat means that there's no structure to it. Every destination has its own place. Hierarchical means that you can summarize a whole bunch of destinations into one table entry. So flat is convenient for moving things around without having to change your address, because if it's flat, it doesn't have anything to do with where you are, whereas hierarchical makes the forwarding table smaller. So a label is sort of a path. So here, this is how label-based works, that it's a pair of input port and this label, which changes as the packet is forwarded, and it's only of significance on a particular link. And so the forwarding table is based on the pair of input port and label, and it tells you which output port to go on and what to replace the label with. So that's how MPLS works, that's how ATM worked, how X25 works. So if you look, there's a path from A to D. When A transmits the packet, it puts in the label 8, and then when R1 receives it, R1 in its table says, if I get something on port 4 with label 8, I should put it out port 7, that's the middle entry there, and replace the label with 92. So now the thing has the label 92, and R2 receives it, and it says, if I get something on port 2, so that port R2 thinks of as 2, with label 92, I should forward it out port 4 and replace the label with 8. And so that's how that works. So you could do it either way. What are the pros and cons? And the third way is flow-based, where an entire conversation, and how do you define a conversation? It's not just a source and a destination IP address, but it's also TCP ports. So, and if you have you could have a separate forwarding table entry for every single flow. So some thoughts. If you're going to do it based on a destination versus a label, it seems like with destination address, your forwarding table is smaller because it's proportional to the number of destinations, whereas with the label, it's really a source-destination pair. So you're going to have the square of the number of table entries. People think that the reason that we're doing this MPLS kind of thing is because of doing what's called traffic engineering, which is locking down certain paths. But that really has nothing to do with it being this number that changes hop by hop. If you wanted to lock down the path, you could just lock down the forwarding table entry to that destination, or you can make special destination addresses that are those paths and have other entries be, kind of traditionally to various destinations. ATM did this thing based on labels, because the assumption back then was that it was for telephony, and the number of telephones was like way bigger than the number of currently communicating telephone pairs. So you could have a much smaller thing in the header if you were talking about the current conversation going on between these two guys than if you actually wanted to address the individual destination. So they were assuming that the number of pairs that are currently talking was way smaller than the number of nodes attached. They were also assuming that it was okay to have a latency before you start up a conversation. Because like in telephony, you're expecting to like dial the phone, and it takes a while, and you expect that. But in a data center, it doesn't seem like either of those assumptions make any sense. You want any pair of nodes to be able to just immediately talk. MPLS did it with this label because it started out with this kind of thing called tag switching, which was that some vendor thought it was too hard to parse an IP packet. So what they did was when they received an IP packet, they said to their neighbor that sent it to them, hey, would you do me a favor, and in the future when you send me a packet like this, would you put this little shorthand in there, and I'll know which table entry it is, so I don't have to go parse the whole packet. But it could have been done with this extra header with the destination rather than this thing that changes hop by hop, and I think it would have been superior. Yes?
Is it the same end in your first sub-bullet for the OMM forwarding table and the label-based?
Right. If you have n sort of destinations, your forwarding table will be O of n. They'll be like proportional to the number of destinations. Whereas if it's with a label and it's for every pair of things, then the forwarding table is the square of that.
I guess I'm asking, how are these two technologies used? So, like if you're doing IP routing in the core, maybe n is the total number of prefixes in the global internet, and maybe n is something much smaller for label switching, like the number of border routers in your AS. So I'm not sure it's an apples to apples comparison.
Right, right. So I mean, this is sort of, I'm being thought-provoking. Yeah, but okay. So another kind of thought is flow-based, where you want to have a separate forwarding table entry for every flow. And the idea is to kind of move the traffic, spread it around with different flows in different places. But if you imagine your forwarding table based on every conversation going on, your table will be huge. And the only way to actually make this work is to create a table on demand, which is kind of, will cause a lot of overhead. So if you want to exploit parallel paths, it would be really nice when S is talking to D that it can send to any one of the R1 things, and then that one can send to any of the R2 things. And it would be really nice if it could just sort of send it on the shortest queue. It's in a great position to know what's going on right now. Okay, and load splitting, this is, the introductory stuff is not as funny, so I should try to get, people are not smiling, they look tired. Load splitting, when you want to spread the traffic around and you want to keep packets in order, you can't have a switch just send things on the smallest queue. So one possible way that technologies do it is where the source has multiple different addresses to call the destination, and each address is a different path to the different destination. And so to spread the traffic around, you can talk to the destination with different addresses, and each one will take a different path. Or you could have a forwarding table based on every flow, which means for a particular conversation, all the packets will go the same way. Or you could do what kind of traditional IP routers do, which is that they look at other information in the packet to choose which path. So they identify the flow by looking further into the packet to look at the TCP ports and do some sort of hash. So even though there's 4 possible ways to go, they'll deterministically always choose the same path for the same flow. So here's a research suggestion. Suppose there's a central place that knows all of the conversations going on. In which way will traffic get spread better? if there's a central place that carefully engineers the paths for every flow, or to just have this simple, small forwarding table based on destination address and let the switches make a decision. And so the switch might kind of deterministically choose which of 4 ports to send things on based on some hash. But I mean, ideally, it wouldn't have to worry about order in every single packet it could do. But if it has to keep things in order, at the very least, it could notice that some queue is getting longer and change the hash. So occasionally it moves more flows and spreads it around better. My feeling, it seems like a lot of people kind of believe that a flow starts out at constant bandwidth and kind of lasts for hours. So you have like all the round trip times in the world to kind of gradually change, the amount that it's sending. I think, especially when you're going to these huge speeds in the backbone, that you have zillions of tiny little flows that are like incredibly bursty. And people say, well, what about video? And it's like, yeah, video. But on the other hand, with compression, even those things should be bursty. So anyway. So yeah, it seems to me that it would be a better design to give the switches the choice of how to spread the traffic around. And I believe that flows are inherently bursty. So, okay, so a completely orthogonal question is, where does the forwarding table come from? So you could have a distributed algorithm, or you could have a central node that somehow receives information about what links are there and stuff, and it calculates topologies for everybody. Neither thing is new. ATM did it based on a central thing, and InfiniBand does it based on a central thing. The internet kind of does it based on distributed algorithms, usually. Some people say, well, if we get rid of the distributed algorithm, suddenly switches will be infinitely cheap. And I'm not sure I believe that. I think that the reason switches are expensive is trying to engineer a box that can move that much data that quickly. And the actual sort of distributed algorithm by which you gossip with your neighbors and figure out how to fill in the forwarding table, I don't think that's the reason that switches are expensive. So it seems to me the distributed algorithm would be superior because it reacts more quickly to changes. And why is that? When a link changes with what's called the link state algorithm, information about the change propagates outward from the link change as quickly as physics allows it to propagate. And everybody, as this information goes through, can update their own table. Whereas with a central thing, somehow you have to assume you still have a path to the central thing to let them know the topology changed. The central thing has to recompute everybody's paths and then has to go touch everybody to update their tables. So it seems like it, but anyway, it could be that if there's very few topology changes, that a centralized thing would have less overhead. Who knows? And this is a really mysterious thing to me. I never paid too much attention to how you manage a network. Every time you do a protocol, there's this thing called a MIB, which says all the parameters in that protocol that are readable and writable and whatever. And it used to be you'd even say the word MIB, and I'd be like sleepy. I just didn't want to read these things; they were boring. And so the way that I understood how networks worked, I had been actually to a network operations center, is there was one room with one management console with a big screen that kind of showed the whole network and what it looked like, with links that were green if they were happy and blinking if they were down or something like that. And the network manager typed big commands, whatever he wants to do to control the network, at this one machine. And it would turn it into management commands. There was a standard called SNMP that would be able to talk to each of the switches, and according to this MIB that would decide what parameters were readable and writable. So then recently people have been saying, oh, wouldn't it be great if you could manage a network from one central place? And I said, isn't that how it's done? And they said, no, what you do is you have to actually like connect via like telnet to each individual switch and talk to it in the command line interface of that particular vendor. And that's like horrible. Why would anyone do that? Well, it, you know, kind of recreating historically how we got away from this, you know, simple vision of how it should work to this horrible scenario today is that apparently, you know, there's supposed to be this MIB for everything that's settable and whatever, but then these vendors come up with these proprietary stuff that is not manageable via the standard. And you could either blame the vendors for not making their stuff available through the, you know, giving them object identifiers in order for the management station to talk to it, or you could blame the standards bodies for refusing to put in proprietary stuff until the standards body has. But whatever, we've kind of gotten away from that vision, which is really kind of sad. Right, to my astonishment, that original vision degraded, but now people are saying, oh, shouldn't we like invent this vision? So yeah, that's a great vision. Suppose we reinvented it at this point, and someone said, okay, now we're going to define exactly, we're going to standardize what things you say to a switch. Well, if we were to snap our fingers and do that again, I have no idea why you need to invent a new language for talking to the things rather than SNMP, but I don't care. It's just syntax. You have to somehow relay what you want to set and read and whatever to the switch. But is there any reason why the world wouldn't degrade again for the same reasons as it degraded the first time? I don't know. But yeah, network management is not my thing. So new topic. Okay, so this is the thing that probably people think I was really going to talk about. So what is Ethernet actually? You know, everyone thinks, wow, Ethernet was like really successful. No, it died out decades ago. There's something that you call Ethernet, but it has nothing to do with the original invention. So yeah, what's this whole thing about layers 2 and 3? So people argue about, should we do layer 2 or should we do layer 3? So let me explain what layers are, and I will talk about Perlman's view of the layers, which is, you know, based on the ISO view of the layers. ISO sort of came up with this model originally. So Perlman's view is that layer 1 is the physical layer. You know, it says how you signal a bit and what the cable looks like. Layer 2 is how you send a packet of information to a neighbor. So somehow when sending bits, you have to signal this is the beginning of a packet, this is the end of a packet, here's a checksum. You know, that's layer 2. It's only supposed to be to your neighbor. Layer 3 is the thing that creates an entire path and forwards packets and so forth. Layer 4 is some sort of end-to-end thing that puts packets back in order if the network gets it out of order. And layers 5 and above are boring. That's why it's Perlman's view. So why are we forwarding Ethernet packets? The way that I just described it, Ethernet is layer 2. It was only supposed to go to your neighbors, so why are we forwarding this? And the only way you can possibly make any sense out of this is to understand history, because there's no logic, there's no rational world in which we would have been forwarding Ethernet packets. So how did it happen? What exactly is Ethernet? So back then, before Ethernet, I was the layer 3 architect for DECnet. So I was in charge of designing the routing protocol. And you know, mostly layer 3 were point-to-point links. And then along came the Ethernet. And so I said, oh, interesting. Now we have a new kind of link on which you can have hundreds of neighbors. And the way I had done the routing algorithm, this would explode, you know, it would not scale well. And so I just had to rethink the routing protocol to take care of this new kind of link. But unfortunately, the world just got confused. And they thought, because Ethernet was like so hyped and stuff, this was the new way to do networking. So they were, you know, building their application directly on Ethernet without layer 3. And so I was saying, no, you don't want to do that. You still need layer 3. And they were saying, oh, you're just upset because no one needs your layer anymore. And I said, I mean, Ethernet was designed just to work within a building or something. I was saying you might want to talk from one Ethernet to another. And they said, our customers would never want to do that. So the industry built all this stuff leaving out layer 3 just because they were confused. Ethernet kind of looks like a network protocol. There's an envelope with a source and a destination address. So it started out with this thing called CSMA CD. So well, I'll get to that in a minute. But what an Ethernet packet looks like is you put your data in an envelope. So this kind of looks like an IP packet. There's a destination and a source. Something that's missing is a hop count, which IP has so that in case there's a temporary loop, you'll get rid of it. There's nothing in here for Ethernet. Is it because it didn't occur to them? No, it's because it never occurred to them anyone would be foolish enough to be forwarding based on this thing. It was intended only to be on a single link. Ethernet, the invention was CSMA CD, which is like a really cool protocol, which I noticed I have like ingrained into my being. So CS is carrier sense, which means don't interrupt. If someone else is talking, don't talk. MA is multiple access, which means be aware you're sharing the air. CD is listen while you're talking in case somebody talked at the same time and you back off and you decide who talks. When I'm at meetings, I sort of notice I cannot interrupt somebody. So I just sort of have to do CSMA CD, whereas other people who I guess are not networking people, they just sort of talk whenever they feel like talking. And then there's the people that kind of wait until the end of a sentence. And I try to jump in at the end of somebody's sentence, and some people have adapted so that they never actually finish a sentence. But at any rate, there's lots of papers about the useful throughput that you can get when things are heavily loaded is only about 60% because of all the collisions. And people quote that to me. They say, oh, Ethernet, you can't get more than 60%. And it was also limited in terms of the nodes and all that. So here are these perfectly good academic papers showing something like you can't get more than 60%, but they're completely irrelevant because Ethernet hasn't been CSMA CD for decades. So as I said, people got confused and thought Ethernet was a network instead of a link, and they built applications on Ethernet with no layer 3. You can't use a traditional router which forwards packets without the end node cooperating by putting in the right envelope, the right layer 3 header. So from around 1983, my manager said to me, Radia, we need to design some sort of magic box that sits between two Ethernets and lets somebody over here talk to somebody over there. And that's, like an IP router or something. But the constraint was without modifying the end node to put in layer 3 or modifying the Ethernet packet in any way. So that was sort of the problem being constrained. So the basic concept was that you have this, this green circle that listens promiscuously. It listens to every single packet that it receives and stores it up. And then when the ether is free on the other side, or if it's a token ring, when it gets the token on the other side, it forwards it. So this basic idea of just moving Ethernet packets around works just fine unless there's loops, in which case nothing's going to stop the packet. There's no hop count. And it can actually be more clever than that, and it can remember when it sees a packet over here, it looks at the source Ethernet address and says, so he must be on this port. And so then if he receives a packet with the destination address being a guy he learned was on that port, he doesn't have to forward it at all. So here he's learned that A is over there. If A sends a packet for J, he doesn't know where J is, so he has to forward it on those ports. If A sends a packet for X, he's learned because X talked before, and so he can send the packet just on that port. Or if X sends a packet for C, he doesn't have to forward it at all. So you have this physical, oh, right. And so my manager, posed this problem to me, saying, so you plug the thing together, and you somehow want these switches without any configuration to figure out a loop-free subset, so you can just do this simple algorithm of moving packets around. Now, something I should say is I hate technology. I'm totally befuddled by cell phones and cameras and all this kind of stuff. So when I design things, the way I would like it to work is it just works, and you don't have to understand it at all. And eventually, people kind of explained to me, no, Radia, there's some customers that really want knobs to diddle and feel like they're really controlling things. So now my philosophy is, fine, I will still design it so you don't have to touch anything. But if you want to touch things, I'll give you knobs to diddle, and any setting of the knobs will still work. So, so at any rate, he was asking me to do this spanning tree thing. And the story of it was that he asked me on a Friday, and he was going to be gone the whole rest of the whole next week. And he also thought it was going to be really hard. And so for some reason, he decided he would be like witty, and he'd say, well, I'm giving you this impossible problem. Why don't you take it as a challenge to make it scale as a constant? So no matter how many bridges and links there are in the world, the amount of memory necessary to run this should be a constant, which is absurd. Nothing is a constant. It might be linear if you're like really lucky. But then he went away, and it was unreachable, and this was before the days of, cell phones or emails or electricity or, whatever. And so he, that night I realized, oh my goodness, it's trivial, and furthermore, it scales as a constant. Because if you run the spanning tree algorithm, what you need to do is remember on each of your ports, if you have 5 cables coming out of you, you have 5 ports, you have to remember the best spanning tree message you've seen on each port. So all you have to do is kind of be receiving messages, and if you receive something that's of type spanning tree message, you compare it with the one you have stored, and whichever one is better, that's the one you keep. These messages are about 50 bytes. So if you have 5 cables, it takes 250 bytes to run the algorithm. So, and it was such a dead trivial algorithm. Everything I've ever done, by the way, is dead trivial. So that night I realized exactly how to do it, and that it was obviously going to work. I spent Monday and Tuesday writing the spec in enough detail that the implementers got it working in about a month or 2 without asking me a single question. And the remainder of the week, I couldn't concentrate on anything else because my manager was away. So I spent the rest of the week working on the poem that goes along with the algorithm. So I'll get to that in a minute. So what the spanning tree algorithm does is it takes this physical topology and prunes it to be loop-free. So it decides which ports to turn off. So the circles are bridges. These are Ethernets. And these are ports. And those are ports that the spanning tree algorithm turned off. So this is the poem, which actually was the abstract of the paper that I published about this. And it really describes the algorithm, everything you need to know about it. So it's called Algorhyme, because every algorithm should have an Algorhyme. I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity, a tree which must be sure to span so packets can reach every LAN. First, the root must be selected. By ID, it is elected. Least cost paths from root are traced. In the tree, these paths are placed. A mesh is made by folks like me. Then bridges find a spanning tree. So, and then there was this great story about the implementers wanted to build the simplest possible device. And as trivial as the spanning tree algorithm is, it still made it more complicated than just what they wanted to do, which was tell the customer not to put any loops in the topology. And so I didn't want to argue because, I felt like people wouldn't believe me anyway because they'd think I was, biased. But as it turns out, management told them, yes, you have to put the spanning tree in. Well, when they sold the very first bridge, I was still sympathetic with them that maybe a simpler device would have been the right thing until they sold the very first bridge. They sold the very first bridge to the world's most sophisticated networking customer, who had the world's simplest topology, which was 2 Ethernets and 1 bridge. And I found out later, the salesperson was trying to explain this thing, and the customer was saying, oh, but they're doing all this complicated stuff. And the sales guy was saying, oh, it doesn't matter what you're doing, it's just going to work. And they said, oh, we need to talk to the engineers. And the sales guy said, no, you don't, it's just going to work. So they put it together, the 2 Ethernets, 1 bridge. It didn't work, and they were really angry. And when the field service went to figure out what the problem was, they realized, again, the most sophisticated customer in the world, world's most simple topology, had done this. And actually, everything was working perfectly. The spanning tree algorithm said, I don't need to forward, but if I ever do, I will. So the problem with spanning tree is you get suboptimal paths, and some of your links are not used. If you look at the path from A to X, it goes through 11, 7, 6, 2, 14, 4, 3, and to X. And so that's like a really long path. And you might think, well, if it were just a smarter spanning tree algorithm, you would have come up with better paths. But no, once you decide you want one loop-free subset, there's going to be suboptimal paths. And the easiest way to think of that is, suppose your network is one big circle. The spanning tree has to cut it someplace. And if you're on either side of the chop, you have to go around the long way. By the way, when am I supposed to end?
Probably about 5:15 at the latest.
Oh, good. OK, so I have enough time to go through this. Yeah, I was kind of taking too much time on that. Right, why not just use IP routers? So now everybody does have layer 3 in their stacks. So why not get rid of all this spanning tree stuff and just put in IP routers? And the reason is something that you will never get from one of these books that tell you that everything about IP is just magnificent and perfect, is IP is not actually a very good layer 3 protocol. It's just like English might take over the world, but it's not because English is like the best language around. If it does take over the world, and you're trying to analyze it, and you say, well, of course it's better than Dutch. They have too many consonants, or something. But there was just kind of a historical reason why it wound up being IP. That was kind of the one. But IP has actually an annoying property that every link has its own block of addresses. So if you have a block of IP addresses and you want to assign addresses to your building, then you have to chop up the address space. You have to configure the routers to know which addresses are on which ports. And if a node moves, it has to change its address. Now, that's how IP works. It's not how layer 3 has to work. There were layer 3 protocols that did not work that way. So, for instance, CLNP, which was ISO's version of IP, that DECnet adopted as their packet format, because they said, we don't need to, we want bigger addresses, and hey, rather than inventing our own format, let's just adopt this thing. It had a 20-byte address where the top 14 bytes were prefixes, the prefix that was owned by all nodes inside of some big cloud. And the bottom 6 bytes were your end node ID inside the cloud. So as long as you stayed within this cloud, you could move around and keep your address. And the way this worked was that the end nodes in the cloud let the routers know where they were. So a router would say, is this the prefix for my cloud? If so, I will route based on that part and send it. Yeah, if you have one prefix per link, like IP, you have to carve it up, and if you move around, you changed it. And these guys, the switches have to be configured with where everything is. If you do it this way, switches need no configuration. You can move around and keep your address. And so this is sort of a much nicer way to do it. Well, the single worst decision in the history of mankind was that in 1992, people said, hey, you know, the IP address is too small. Why don't we replace it with ISO's version, which has a 20-byte address? And people just went berserk. You know, it's like, oh my gosh, you'd be ripping the heart out of the internet and putting in this foreign substance. Yeah, and imagine if there weren't this resistance. If they had done this in 1992, we would have had bigger addresses by now. The internet was a nothing little researchy thing in 1992. You know, CLNP was implemented by all the vendors. People demonstrated you could run TCP on top of it. It just would have been trivial. These days, it's so hard to change the internet. It's so mission critical. So will we ever get to IPv6? Well, and worse than that, if you take another 20 years to design something, you would hope that it would be orders of magnitude superior to the thing that you rejected. No, it's not. It's just kind of bigger addresses. And worse yet, it's kind of worse than CLNP in some very important ways. Like IPv6 still has the property that every link has its own prefix, and you have to configure all the switches and if you move around, you change your address. So we're kind of stuck with keeping Ethernet around as kind of a large cloud that looks to IP like a single link. So what we're doing is, instead of CLNP having this lowest level that's kind of a flat cloud, we're doing it with Ethernet. So you want a large cloud with a flat address space, but you don't want the limitations of spanning tree of sort of suboptimal routes. So the next step in evolution is this thing called TRILL, which stands for Transparent Interconnection of Lots of Links. So the basic idea is that you actually put your Ethernet packet inside another thing. Oh yeah, I said I believe in making things auto-configure and giving people knobs that they can't hurt themselves by playing with. I also believe that instead of telling people, throw away everything you have, here's a new architecture. I think you're much more likely to succeed if you can take what's out there and say, here are fancy new boxes, that the more of these fancy new boxes you add to what you already have, the better things will get. And so indeed, that's how TRILL works. It's evolutionary. You can take a spanning tree-based Ethernet, replace any subset of your switches with TRILL switches. And the more switches you replace, the better bandwidth you know, the more multi-pathing and shortest paths and all that you can get. But you don't have to throw away any of your existing stuff. So it involves putting your Ethernet packet into another header. So A transmits an Ethernet packet. These are TRILL switches. So the TRILL switches kind of talk amongst themselves, and they actually assign themselves what I call a nickname, which is a 2-byte address. And so it puts it in this envelope. That's this very simple 6-byte header. That's the 2-byte address of the source, R1, the 2-byte address of the destination, R2, and a hop count. So then it's very much like a layer 3 protocol with 2-byte addresses. But the 2-byte addresses you don't have to configure. They just sort of create their own. And what's nice about this is the guys in the center don't have to know about where all the end nodes are. They just have to have a forwarding table, which is the size of the number of TRILL switches. And once it gets to the last TRILL switch, the last guy removes the Ethernet header, the TRILL header, and out pops an Ethernet packet. So A and C don't know that they're doing anything different than just talking Ethernet. So this is what a TRILL packet looks like. You have the original packet, and you have this extra 6-byte header with who the first switch is, who the last switch is, and a hop count for temporary loops. So this 16-bit TRILL switch nickname is a little worrisome in terms of scalability. It allows 64,000 switches. You can have many more end nodes than switches, but you know, is 64,000 enough? Well, that's pretty big cloud, actually. What's nice about 64,000, rather than making it a 4-byte address, 4-byte flat address, is that you can imagine a dense forwarding table that you just do a simple lookup. Because 64,000 entries is not that big. Whereas if you made the address much bigger, your forwarding table, if you wanted it to be a simple lookup. So the advantage is the extra header. The switches inside don't need to know about all the end nodes. Just the first switch has to know that it's the right last one. So how did R1 know that to get to C, he had to send it to R2? And this is kind of an orthogonal thing to the rest of TRILL. You could do it like bridge Ethernet learning does, which is that if R1 doesn't know where it is, it sends it through a tree. And when guys decapsulate the packet, they remember, they look at the source address, which is A, and the first switch, which is R1, and have this learning table that learns based on received traffic where guys are. So you could do it that way. You could configure it. I've talked to cloud people who say, no, they want to absolutely configure everything. They don't want random MAC addresses coming. And you could do it that way. Or you could have some sort of directory where if this guy doesn't know where it is, he goes and asks, for instance, the DHCP server and says, you hand out IP addresses. Instead of my forwarding this ARP, tell me who you handed this ARP to, and tell me, furthermore, what switch it came from. And you could do it that way as well. And it's evolutionary, as I said. So now, OK, orthogonal concept. Who puts on the header? It could be the first switch, or it could be the hypervisor, or it could be the virtual machine or the actual application. For just sort of getting it deployed quickly, it's nice if it's the first switch. But pushing the work of learning the correspondence of where the destination is as close to the application as possible is better because it saves work for the switch. He doesn't have to keep such a large table. And the switch is not in as good a position to know whether the destination has changed and he's sending it into a black hole as the source hypervisor would be. My son was well familiar with the Algorhyme poem because my daughter is a musician, and she plays violin. I've always been her pianist, and then she started singing opera. So she was doing a recital once, and I was her accompanist for it. She was singing all these Italian arias and stuff. And my son, for fun, set the Algorhyme poem to music. And so that was one of the arias that she sang. So I was giving a talk about TRILL, and I was deciding, hey, there's not enough jokes here. So I called up my son at 10 o'clock at night, the night before I had to fly out to go give a talk about this. And I said, look, I want to have a version of the poem that describes this new thing. And you have 1 hour to work on it. And I'll call you back in an hour. If you've done a good enough job, I'll use it in my talk. And if not, hey, all you've done is wasted 1 hour of your life, and you owe me that much. So I called him back in an hour, and he did such an excellent job that not only did I use it in the talk, but it's actually in the spec. And there's just one word I have to explain, which is that these TRILL switches, in the original paper, I called them R bridges for routing bridges. I don't like that term anymore because when I try to explain it to people, they think I'm saying OUR bridges, our bridges. So I try to say TRILL switches instead, but then the poem doesn't work, whatever. So Algorhyme version 2 by my son. I hope that we shall one day see a graph more lovely than a tree, a graph to boost efficiency while still configuration free, a network where our bridges can route packets to their target land. The paths they find to our elation are least cost paths to destination. With packet hop counts, we now see the network need not be loop free. Our bridges work transparently without a common spanning tree. So recently, there's been a bunch of similar things invented, and this happens all the time where suddenly there's this stuff. So it's like NVGRE and VXLAN, they're basically the same sort of thing. You take you know, some sort of flat address space, and you put an extra header on it. And these things are based on IP. So VXLAN is an IP header with a UDP port and extra information. NVG, you know, it's just a big header. I tried to talk to somebody who was all excited about this, and I said, it's basically the same thing as TRILL, but just with a less efficient header. And he told me, no, no, no. TRILL is doing tunneling, and this thing is doing encapsulation, or vice versa. I don't know which was which. But anyhow, the way that I think you ought to think of it is that there's an inner packet based on a flat address space. Now, some of these things use Ethernet as the flat address space. Others use IP. I think Ethernet as a flat address space is superior because it's a bigger address and a smaller header. Everyone knows how to get unique Ethernet addresses, but unique 4-byte IP addresses, well, you know, that's more configurations. So I like having Ethernet inside. And as for the outer header, the TRILL header is this nice 6-byte thing where you can do a fast lookup, whereas these other things, you know, with these big IP headers and stuff, you know, it's just seems less efficient. But anyway. Okay, so here's a kind of an interesting note. If you compare CLNP, if you remembered it, the 20-byte address, versus using IP to get to the cloud and then the TRILL thing, if you used CLNP, you don't need to do this ARP thing at the last hop in order to make a correspondence between the layer 3 and the layer 2 address. So in that sense, TRILL, CLNP would be better. But if you do IP plus TRILL, then the forwarding table inside the cloud is smaller because you only need to have it be as big as the number of switches, whereas CLNP, you had to keep track of all of the end nodes in the cloud. So, okay, so this is like, we're almost done. So this is just sort of obvious stuff that everybody gets wrong when they're designing protocols. You know, and it's like insulting to you to even tell you about it, but yet people go off and design things, and they're getting it wrong. So here's a question. What's a version number? Well, before I ask that, what's the difference between a different protocol and a different version of the same protocol? You know, that's a philosophical thing. The way that I would define it is that, I mean, you know, like for instance, if you'd done CLNP to replace IP, was it ripping the heart out of the internet and putting in a foreign substance, where IPv6, hey, it's just a new version of IP? You know, it's, right. So to me, if you're sharing the same Ethernet, ether type, and you're telling the difference between the two protocols based on a version number, then it's a new version of the protocol. If you have to change the protocol type in the ether header, the ether type, then it's a different protocol. You know, or at higher layers, if you're using the same sort of well-known port with a version number, then again, it's a new version. Whereas if you have to use a different port, then it's a different protocol. But somehow people think they put a version number into the packet, but they seem to think that it's decoration. And so in the spec, they say, here's an IPv4 thing, and here's a version number field. Put a 4 there. End of story. Well, you can't differentiate based. The only way that this version number thing can work is if you say, put a 4 there, but when you receive something, check if it's a 4. If it's not a 4, throw it away, because who knows what they did in the new version. You know, the fields can be all in different places. But since they didn't do that, the problem is that IPv6 is not a new version of IPv4. It's a totally new protocol, because they realized that when they sent an IPv6 packet using the same ether type to an IPv4 node, it just happily decided, oh, these 4 bytes are the destination address, you know, and it, you know, did who knows what. So indeed, IPv6 is not a new version of IP. It's a new protocol. It has to have a new protocol type. And you would think that they would learn from that, and the IPv6 spec would say, put a 6 here, And if it's not a 6, throw it away. But no, the IPv6 spec says, here, put a 6 here. So there's never going to be a new version of IPv6 either. Now, there's other things that, I mean, not only do you have to say, don't try to parse it if it's an unknown version number, but also if you are trying to do this trick of using 2 different incompatible things with differentiating with version number, you have to keep the version number in the same place. You can do anything else you want with the packet, but the version number has to be in the same place. So SSL, when it went from version 2 to 3, they redid the whole packet formats and moved the version number field. So anyway, parameters. You have to minimize, don't have parameters. Every parameter you have to document it, people have to read about it and whatever. So it's better to avoid them, have things be self-configuring or figure out a constant that works and just set it to that. But if you do have settable parameters, you have to make sure that they can't be set incompatibly across nodes. So it's easy enough to say when you're setting this node, there's a legal range. But it's possible that 2 nodes will have different legal numbers that don't work together. So a great example of that is a protocol that I was never able to explain to my otherwise bright college-age son, which was there's no such thing as a reliable I am dead now message, so you have to periodically call your mother. And here's an opportunity for a parameter mismatch, which is how frequently you call your mother versus how long she waits to call the police. So indeed, in ISIS, what I did in that protocol was that, and this was something just seemed so obvious, I never wrote it down other than just designing it in. I never wrote a paper about it. I never patented it. So in the hello message, I say, hi, I am Radia. And expect, if you haven't heard from me for 90 seconds, assume I'm down. And I would send hellos about 3 times as frequently as that. So OSPF, again, it's sort of different sports teams. They said, oh, wow, we want a protocol like that, but we need to design it ourselves. There was sort of no reason why they needed to. So they kind of copied ISIS, and they noticed this field where you pass along this parameter. But what they did with it was, they say, hi, I'm Radia. I send hellos every 30 seconds. And the receiving node says, oh, cool. Let me compare that with my own hello timer. Oh, my hello timer is every 25 seconds. I refuse to talk to you, which just makes the network like really brittle. Why shouldn't you have the things set at different nodes? But anyway. Latency. So this is another, I think this is the last. Right. So if you want a packet to get there really quickly, then from source to destination, what a good thing to do is for a switch to start forwarding before it finishes receiving the whole packet. Store and forward means you receive the whole packet, and then you start forwarding. Cut through says as soon as you can figure out which port this should go on, while you're still receiving the rest of the packet, you're forwarding it. So that's called cut-through. So it's nice to be able to do cut-through. What field do you care about in the header that would make you be able to make the decision about which port to send it on? Well, the destination address, right? So let's look at the IPv4 format. So, well, version number, internet header length, type of service, all this stuff. The absolute last thing is the destination address. I could just see the committee where they're meeting, where they're trying to write down on the board all the things that might be important. And then when they're almost ready to go and someone says, you know what would be useful? A destination address. Sure, and they add that to... well, so let's look at the IPv6 packet format. Again, the very last thing is the destination address. Another latency mistake, TCP has a checksum in the header, which is over the data. So that means that if you have some data that your NIC or whatever is trying to forward out, it can't start forwarding until it sees the whole packet. So it can compute the checksum to put into the beginning of the packet before it sends it. So, so parting thoughts. Don't believe anything about technology X unless there's a plausible inherent reason for it. So if someone says X is, higher throughput than Y, don't repeat it, don't believe it unless you can figure out some intrinsic property of X versus Y that would make that true. Because often when people say that, it's just not true. Don't get carried away by buzzwords, unless you really know what they mean and whatever. And then this is sort of the anecdote that I'm sorry if you've heard it before, but it's sort of my favorite anecdote. It's absolutely true. In my book, I try to illustrate the points I'm making by these little boxes I call real-world protocols to illustrate the point I'm trying to make. So one of the problems in this industry is that people don't start out knowing what problem they want to solve. They just immediately get excited and start writing code for the few special cases they can think of. More cases come along and they write more code for those things, and this thing just sort of grows. I actually think it's much better if you start out thinking very hard about what exact problem you want to solve, and you'll come up with a much better solution. So the anecdote that will forever cement in your mind that why you should know what problem you should be solving before you try to solve it is that when my son was 3, he ran up to me crying, holding up his hand, saying, "My hand, my hand." So I kissed it a few times. "What's the matter, honey? Did you hurt it?" And he said, "No, I got pee on it." So, thank you.
For a number of questions. So very nice questions for Radia, for words of wisdom.
I've intimidated you all. Yes?
So there's I don't know if you're familiar with the TRILL and
Yep.
There's a new drive in recent years. I was wondering what your opinions. Do you think it's going to allow more creativity?
Okay, well, honestly, everywhere I look, I see all these papers, and I see entire conferences, that basically say, what a privilege it is to be born at this point in history when software-defined networking is transforming the planet. And I'm not exactly sure what's new there. The notion of open flow where you have a forwarding table entry for every single flow seems to me that there's this latency when you create a flow. This whole thing that I asked about earlier, which is, do you really get much better utilization of the network if there's a central thing that knows about all the flows and carefully, versus letting the switches do it? I think that before we just sort of get swept away with the excitement that the world is being transformed and, like hunger will go away and, all this wonderful stuff because of this great new technology, it would be good to kind of soberly study this stuff. Software-defined networking, to me, it's like 3 words. I know what all 3 words are. I'm not sure what they're doing in the same phrase. There's a lot of things that people talk about, that think about when they're doing it. One is this vision that you control the network from one place, which, as I said, was the way that, of course, it should work that way, and I was surprised that it doesn't. So that's a good thing. Whether you have to reinvent the protocol talking to the switches, I don't know. I don't really care. That's just syntax. It's not my layer. It's in the layers 5 and above, which are boring, But another thing that people mean is using a general purpose machine as a packet switch. Well, that's how it used to be until bandwidth got so fast that they had to kind of engineer special boxes. But these days, with like massively parallel, lots of cores and lots of threads, and forwarding is sort of inherently parallelizable, we can go back to that vision, and that's great. As a network person, I don't care what's inside your box. If you can make your box out of, smart little mice that are moving things right, I don't care. If that's the most cost-effective way to do it, that's great. Yeah.
As an engineer, would you say that you were slightly disappointed by the fact that people have picked up on TRILL-like ideas DX and repaired and whatever, that they have taken those ideas and then made them proprietary so that nobody else can interoperate.
Yeah, well, that's a problem. So, yeah, people kind of take it, but don't quite do the standard. But supposedly they promise, and supposedly it's actually been the case that now it can be the standard as well. So, I mean, I know in one case it was because the company had a similar idea before, and then they saw TRILL and they said, yeah, actually this is a good way to do it, but didn't change their packet format. Yeah, somehow, I don't know how SDN got this amazing hype across the industry, and almost never, no one has heard of TRILL. It's sort of, that was kind of why I was pleased that people wanted to hear about it. But yeah, and then there all this VXLAN and NVGRE. I don't see anything in there that couldn't have been done better with TRILL. So I think it's sort of a better way of doing things, and so it would be a good way of, even if people sort of don't call it that. I mean, it's not the world's best name, and it's not, the most brilliant packet format. But that whole concept, I would be pleased if it sort of got done. I would like to see it done the most efficient way with the most efficient header. Yeah, right. Yes?
Do you think where TRILL ended up from where averages began, the complexity, the additional, did you see that coming in advance, or did you think there was a difference between what TRILL is from what individual average?
Right, so the original paper was a lot simpler. So an example, the original paper said, gee, if it's a multi-destination frame, compute one single tree and send things on the tree. Well, then people said, oh, but we want to do multi-pathing of multicast. And I was saying, do you have that much multicast that you really care? And, oh, yeah, some applications that do that. What applications? Oh, can't tell you, whatever. Fine. So as a result, TRILL calculates multiple trees, and the first guy who injects it, in a unicast packet, it's sort of obvious who the first switch is and who the last switch is. In a multi-destination frame, it's clear who the first switch is. Last switch doesn't mean anything. So there you specify which tree. That was a piece of complexity that isn't so bad. None of the pieces of complexity are all that bad. But, like when you keep doing more and more, then it starts to be a lot more complicated. Something that, people want, and I find it terrifying, is when you have multi-homed endnodes. So you could give them sort of their own nickname, but then you'll use up the nickname space. If you have a bunch of endnodes that are all multi-homed to the same set of R bridges, then you can give them all the same nickname, and that's sort of fine. But if you have a bunch of guys who are all multi-homed to R1, R2, R3, and then one of them, their link to R2 goes down, well, they can't be multi-homed to the same nickname as the other guys. You need, sort of a different nickname for other. So yeah, all of these things get to be kind of complicated. I'm not sure if if we were to start over again, would it be any simpler? If they actually want all of these features, I think it's sort of inherent. Yeah, it would be nice if things were just plain simple. Yes?
Yes, so there are two issues which you didn't really bring forward. So what if, for example, you need to keep data about the traffic for the law enforcement purposes, and you're obliged to do it? And what if, for example, you decided that everything should be encrypted?
Right. Well, actually, I don't care. I move bits around. I don't care whether they're plain text bits or encrypted bits, or whether it's wonderful stuff or porn or whatever. I just move the data around, right?
And by the way, there's a contradiction between the two things.
Between what two things?
Encryption and having the data for law enforcement.
Right. Absolutely. So, yeah, I actually once, casually said, because I also love security, that all data should be encrypted end-to-end. And so a friend of mine who works on email said, Radia, if you had your wish, the universe would come to an end. Okay, why? He said, if you didn't have spam filters, you know, at stopping email before it got to you, there's no amount of bandwidth, no amount of disk that can store all of this stuff. So, you know, that's a very interesting problem, that you need these middle boxes to help you out. Yeah, it's like incredibly scary. So, and then this law enforcement stuff. Yes, it's really, what does security mean? You know, a lot of times people say to me, oh, Radia, here's something, add security to it, as though it's sort of like Tabasco sauce or something. And the problem is, what does security mean? So there's certainly a valid definition of security that says, I want law enforcement to be able to be monitoring all of the traffic on the internet and catch terrorists. That's a great thing of security. The other thing is, I want to be able to send a message without anyone else looking at it. And you can't have both. So, yeah, my inclination is for the you know, end-to-end encryption, but then again, you have to take care of the middle boxes. So yeah, it's actually a very interesting question, right? But without a simple answer. Yes?
One last question. TRILL breaks a lot of the basic assumptions by trying to obscure the endpoints. Do you think there's anything when looking at protocol stuff to make that?
Right, so another interesting dimension of security is anonymity, the ability to send something and nobody can trace who it was that sent it. Now, it would be nice, you know, there's one version of security that says, oh, if I'm getting an attack from someplace, I want to absolutely know where it came from. You know, somebody sent a threatening message, I want to be able to trace it back. And the other thing is, I want somebody who is undercover in the mafia to be able to be sending messages without anyone knowing that they're doing it. Again, you can't have both. So Tor, though, is kind of that's something onion routing or something. It's an ability to send things anonymously by sort of encrypting them and putting them in layers like an onion. As far as the network is concerned, that's really just an end-to-end thing. They're just handling, moving the data between one onion router and another. So I don't think it really changes the network all that much. But yeah, then you come up with, do you allow anonymity or do you not? And you can't have both. You have to choose whether you can do one or the other.